Good day, dear colleagues. Theme of my conversation is mm, theme of my conversation is calculation of deflagration appearance in hydrogen-air mixtures, turbulent viscous flow in two-dimensional region. Many researchers devoted to deflagration appearance in heterogeneous air mixes, and transition it to detonation. The preference of heterogen is a fuel is the detonation fuel cycle, which is more energetic, preferable to the ordinary fuel cycle. In connection with this preference, the problem of heterogen detonation agent construction is extremely actual. Using or full in this connection with this, using a full system of kinetic equation allows one to determine moment of deflagration initiations and transition it to detonation one. In this paper, on the basis of also algorithm of viscous turbulent gas mixtures flows with using full system of kinetic equation, numerically investigated flows of reactive gas mixes in some two-dimensional channels with purpose to define condition of deflagration initiations. Equation of chemical kinetics can be write in this one manner in assumption of Arrhenius hypothesis. This is system of full kinetic equation. In my paper, where 9 components of gas mixes was treated, and 11 the most widespread reactions were choose. This is reaction and this is components. Two algorithms were used for numerical solves of system of kinetic equation. The first one was solving on the full system of stiff ordinal differential equation on the basis of numerical GIR method. Idea of the second one is the next. Characteristic feature of hydrogen air gas mixes deflagration is the appearance of sudden explosion after long period of induction. In this induction period, growth of radicals atomic hydrogen, atomic oxygen, and OH appears. Mass of radicals nevertheless stays small, and one of radical components transfers to the others. This explosion mechanism is branching chain reaction introduced by Semyonov. For decision of full system of kinetic equation, in this case, we solve separately system of two differential equations for concentration of atomic hydrogen and peroxide of hydrogen. After that, concentration of other radicals, atomic hydrogen, OH and HO2, Second are found from algebraic relation from assumption of quasi-stationary concentration. And for other large unknowns, molecular hydrogen, molecular oxygen, and water, system of three differential equation is solved with bigger time step. For gas dynamics part, numerical simulation of reactive gas mixes flows during numerical simulation of deflagration appearance. It is necessary to take into account influence of viscous turbulence effects, dissipation, and energy of diffusion with mixed components. In this work, K-epsilon model of turbulence was used. For viscous flows were taken into account dissipation effects and diffusion. The system of equation of viscous turbulent flow and the kinetic equation in the integral form for two-dimensional flows with Sjöström can be presented as follows: the integral form, where unknowns is this one, gas dynamics, K epsilon, and components of mixes components, concentration. After that, we use viscous flows with using tensor of viscosity, laminar of and turbulence at one. This is viscous fluxes, and some formula for viscous fluxes calculation and source terms in the right part of Navier-Stokes equation. This is these very formulas, and numerical algorithm for solving of this Navier-Stokes system of equation is the next. Common features of non-linear TVD and Yannot difference method is calculation of the inviscid flow on the border of finite volume on the basis of approximate state Riemann solvers. In this paper, those approximate state Riemann solvers were defined for arbitrary number of gas mixes, components, and unknowns on the basis of Roy-Pike methods. TVD difference scheme of Chakravarty-Osher of third order of accuracy was used. Modification of this scheme consists of using a pure upwind variant. This variant of scheme made it possible to avoid oscillation of values of radicals concentration during time period of deflagration appearance. For calculation of derivatives on the boundary of the grid cells, for viscous fluxes, Gauss theorem was used. Derivatives was calculated as integral of surface integral of the function. The calculation of those integrals in this paper were provided by the next algorithm. During calculation in viscid flows, with using Roy-Pike method procedures, all unknowns on the bound of calculation cells were already found. So derivatives in viscous flows definition can be found in the center of the cells. After that, we use simple upward choice for defining viscous flows on the boundary of the cell. For using of this algorithm, we used calculation grid. Construction of calculation grid were made on the basis of algorithm of Osa, developed on the basis of decisional system of partial deflation equation of parabolic time. This is example of calculation grid. Every 1/10 linear coordinate linear is drawn on this picture. Only 1/3, only 1/10. And two examples of deflagration appearance in channels with obstacles in viscous terms. The first, flow in non-reflecting nozzle. In this problem, the shock wave propagates initially from the right part of the calculation region. This is calculation regions, and initially this shock wave has intensity of 109, and during this propagation we have the next picture of level lines. This is pictures of level lines for consecutive time moments. We can see that level lines of temperature and water, and in these pictures we can see appearance of water. This means that in places of water appearance, deflagration appears as real result of deflagration. On the bottom, we see two graphics for hydrogen concentration and temperature. We see that diminution of hydrogen concentration show us also deflagration appearance. The second example, flow in channel consists of combination of cylinders and cones. In this problem, again, shock wave propagate from the left part of the calculation region, and during this propagation, deflagration appearance. We see in these pictures level lines of temperature and water concentration, and we can see that appearance of water by level lines show us of deflagration appearance. And these graphics on the axis of symmetry, as in previous problem, show diminution of hydrogen concentration, and graphics of temperature, which is grows during the time in the consecutive time moments. Summary: modification of also algorithm of calculation of initiation of deflagration for viscous turbulent flows of hydrogen air mixes was provided. The inviscid flows were calculated by using pure upwind variant of Chakravarti-O'Share difference scheme. This variant of scheme made it possible to avoid oscillation of values of radicals concentration during time period of deflagration appearance. Calculation of viscous turbulent flows in the center of the cells were made with using values of supplementary unknowns defined on the border of cells as part of Royer-Pike methods of approximation of Riemann problem. After that, upwind meaning of viscous turbulent fluxes were used. The algorithm as a whole provided one scheme for calculation in viscid and viscous flows. Calculation of some problem with initiation of deflagration with hydrogen air mixes in two-dimensional channels were provided. For decision of system of kinetic equation, two algorithms were used. Decision of full system of kinetic equation for multi-stage hydrogen air reactions, and algorithm based on Semyonov theory of branching chain reaction. For calculation, performing structured curvilinear calculation grids were constructed by also algorithm based on decision of system of partial differential equation of parabolic time. And that is references. Thank you for your attention. Thank you for your attention.